Hi everyone and welcome to the internet. What we're going to be doing in today's chemistry lesson is having a look at how we choose the different reaction conditions that we're going to use in any given chemical reaction. Now, what we're hopefully going to be able to do by the end of today's lesson is to explain the appropriate conditions to produce a particular product. So this means that if they give you an example of a particular chemical we want to make and key facts about them, you can then work out what conditions we should use to generate it and explain why. To start us off though, we've got 3 questions on the screen based around our previous lesson, so have a go at answering those 3 questions in your books for me first of all. Let's double check our answers then. So for question 1, increasing the pressure moves the equilibrium position in the direction of the fewest moles of gas. So give yourself a mark if you got that right. Question 2 about our temperature. Increasing the temperature moves the equilibrium position in the direction of the endothermic change. Tick for that one. And finally, question 3, increasing the concentration of a chemical moves the equilibrium position in the direction away from that substance. So 3 potential marks today. Obviously give yourself a mark out of 3 in your books. If you did get any wrong, I'd suggest you write in the corrections so you know the correct answer. So what we're going to be looking at through today's lesson is how we make chemicals that are made through a reversible reaction. Now the reason we're focusing on these ones is because in a reversible reaction the conditions we choose are really important because it all ties into that equilibrium position and where it then falls. What we need to consider is the idea of an equilibrium yield. Now, quite simply, when we talk about the equilibrium yield, this is the amount of the desired product present in the reaction at equilibrium. So what we find is that the equilibrium yield of any given reaction depends on three key factors: the pressure, the temperature, and the concentration. And what we're going to do is we're going to take each of those in turn and have a look to see how we decide which of those conditions we're going to modify and how to modify them in order to maximize the amount of product we make. So make sure you've got those 3 points written down in your books for me. So what we're going to do to hopefully help you understand this a little bit better is we're going to use our example reaction throughout. So what we've got at the top of the screen there then is the reaction itself. So we're going to start off with carbon monoxide, CO, and react that with hydrogen gas, H2, and what we're going to make is CH3OH, or more commonly known as methanol. So this is a reversible reaction. We can tell that from the reversible reaction sign we've got there. And what we're actually going to do is take each of those principles in turn. So if we consider the concentration first of all, if we increase the concentration of the initial gases, so the carbon monoxide or the hydrogen or both, then what we're going to do is move the equilibrium position to the right. Because if we remember what we said last lesson, by increasing the concentration of a chemical substance, the equilibrium position moves away from that. So if we increase the concentration of any of the reactants, then the equilibrium position moves to the right towards the product. So we're going to make a higher concentration of methanol, which is good. What we're really going to be focusing on throughout this lesson is a principle called Le Chatelier's principle. Now, what this really is an observation about chemical equilibria of reactions. So it's the fancy way for saying we're looking to see how we can pick conditions to make our particular product in a particular amount. And what it actually tells us is that when a change is made to a reaction at equilibrium, then the position of the equilibrium moves to oppose that change. So this is bringing in the ideas from the lesson before, where we were looking to see how increasing the temperature, the pressure and so on affects the equilibrium position. What we're now going to be doing is taking those ideas, looking at how obviously changing conditions then leads to the equilibrium position moving to oppose that change, into how we can use this to make chemical products how we want to. So maximising those yields, for example. So there's our reaction that we were already looking at. Carbon monoxide plus hydrogen makes our methanol. What I want you to have a go at doing is in your books writing down how we could change the pressure to get more methanol. So I'll give you a couple of minutes to write your answers to that. So hopefully we remembered that if we increase the pressure, then we're going to move the equilibrium position in the direction of the fewest moles of gas. So if we look at our balanced equation at the top there, we can see we've got 3 moles of gas on the left and 1 mole of gas on the right. So if we increase the pressure, we move the equilibrium position to the right, and therefore we're going to increase the equilibrium yield of methanol. We're going to make more of it. Now, obviously our explanation is just the fact that because we've got fewer moles of gas on the right, then increasing the pressure moves the equilibrium position to the right. So hopefully there you can see how those rules we learnt last lesson are now just coming into play when we want to make a chemical product. Because if we want to make lots of methanol, then we'll be looking and thinking, well, one way we can do this is by increasing the pressure, because by shifting the equilibrium position to the right, that means we're going to produce more methanol in that reaction. So give yourself a tick if you got it right. If not, then make sure you've got those 2 points written down. I'll leave them up for just about another minute. So you might be sitting there thinking, okay, if I want to make methanol, then I'm going to crank up that pressure as high as I can possibly get it. So give me some ideas in your books about the problems of using very high pressures. Just going to give you a minute to just make a bullet point list of any problems of using high pressure. I'm hoping you came up with these two key ideas. The first one, the cost of actually generating these pressures and so on. And the second one is the risk of having things at very high pressures. So give yourself a mark for each of those. One for cost, one for risk. Let's delve a little bit deeper into the ideas about these problems. And if we look at the cost side of things first of all, if we're considering having high pressures, then we do have a cost impact here. Because when we generate and maintain very high pressures, it becomes really expensive. There's a few different reasons for this. So the first one is that we're going to need equipment to actually compress those gases and get the high pressure. And that equipment is expensive to start off with. In order to then run that equipment, we're going to need a pretty decent amount of energy, and any energy requirements we've got in a chemical process has cost associated with it. It's just like when you're at home and you're leaving your lights, your TV and everything on and you get nagged because you're wasting money, then same things here. The more equipment we run and the more powerful that equipment is, the higher our energy costs will be. And then the third and final one associated here is that for the reaction vessel to actually withstand those high pressures, we've got to have these pretty strong reaction vessels, and they're not cheap. So what we see, 3 reasons that using high pressure is expensive. First of all, expensive equipment to generate the pressures. Second one, the energy needed to run the equipment. And the third one, the cost of our reaction vessels that can withstand those high pressures. So make sure you've got those points written in your book. I'll leave it up for about another minute and a half. So when it comes to actually making our choice on what pressure should we use, then as we've said, in our reaction we're looking at, then the higher the pressure, the higher our equilibrium yield will be. But we're not going to just use the highest pressure imaginable, for the simple fact that we're going to use a bit of a compromise here, because we need to balance a high equilibrium yield with our costs and our safety factors. So with our compromise, we're trying to get a high enough pressure to achieve a reasonable equilibrium yield, but not a high enough pressure to be ridiculously expensive or dangerous. Because anytime we've got really high pressure things, then we increase the risk of things going bang, and that's not good. So what we do is we compromise on our pressure, so high enough to get a reasonable equilibrium yield, but not so high as to be expensive or hazardous. So that's our key thing here, and one of the things you're probably going to find in the style of question they ask you on the exam, it's going to be about compromise. So make sure you talk about high enough to achieve a reasonable equilibrium yield, but not too high to be prohibitively expensive or hazardous. So make sure you got those couple of points written in your books. Okay, same reaction still, all I've done is add our delta H this time. So what I'd like you to do is explain how increasing the temperature changes the equilibrium yield. So again, I'll just give you about a minute and a half to do this. Hopefully what we remembered from our last chemistry lesson is that when we increase the temperature, then we move the equilibrium position in the endothermic direction. So if we look at our actual question here, we can see that our delta H has a negative value, therefore it's exothermic in the forward direction. Therefore it must be an endothermic in the backward reaction. So increase in temperature will move the equilibrium position to the left. And as soon as we move the equilibrium position to the left, we're decreasing the yield of methanol. So if you got increase in temperature moves the equilibrium position to the left, 1 mark. If you said that will decrease the yield of methanol, give yourself a second mark there. If you then included your explanation in terms of the exothermic and endothermic, then you can give yourself a third mark, and then give yourself a mark out of 3. Obviously, if you didn't get that, then do make sure you write the correct answer in so you do have that as a record. So once more, what we're going to find is that we're going to have a temperature that we're using in this reaction as a compromise. And the compromise we're going to make as far as temperature is concerned is between the equilibrium position and the rate of reaction. So write down the top sentence for me and then have a go at answering the question underneath. Explain how temperature impacts the rate of reaction. Hopefully we remember from C5, the start of, that we were looking at how temperature affects the rate of a reaction. Now, what we find is that low temperatures have a low rate of reaction, and that's all down to the movement of our particles. So at a low temperature, the particles only have a very limited amount of energy, therefore they're moving slowly. As we increase the temperature, the particles gain kinetic energy, and therefore we get more frequent successful collisions. Hopefully that phrase is coming back to you from some of our earlier lessons. Now, what we need to do is get this balance between a high enough temperature to make sure that the rate of reaction is fast enough, but not so high as to affect the amount of product we're making. So make sure you got that right. Give it a tick if you did. If not, obviously add that detail to your answer. So in terms of the compromise as far as temperature is concerned, then if we were to pick the lowest temperature possible, then yes, of course, we would maximise the equilibrium yield. But it would take a really, really long time, because the lower the temperature, the slower the rate of reaction becomes. If we were to use a really high temperature to get the maximum rate of reaction, we would end up with a really low equilibrium yield. So that's not good either. What we need to do is make sure it's somewhere in the middle. So we need to make sure that it's low enough to give us a good equilibrium yield, but high enough to give us a decent rate of reaction. And it also means that we're not going to have too much cost in terms of the energy demands for increasing temperatures there. So wherever you get a question about temperature, be thinking about those two things. It's about the rate of reaction and the equilibrium yield. It's getting the balance between those. So higher temperatures mean a faster rate of reaction, but in some cases, higher temperatures would mean a lower equilibrium yield. So you've got to get the right balance there. So final thing for today then is the plenary questions. So have a go at answering these questions in your book for me. I'll leave them up for about 4 minutes today, but as always, if you need longer, just hit pause and take as long as you need to answer them.